Section 6.3, similar polygons. We're going to use proportions to identify which polygons are similar and write congruent statements, and we're going to use similar figures to find missing values, and we're going to talk about scale factors. So here we go. So similar polygons are the same shape but not the same size. So this is different from congruent figures. Remember, congruent figures have all angles are the same and all sides are the same, the corresponding sides. Well, here, the corresponding angles are congruent, but the corresponding sides are not. But what we say is the corresponding sides are in the same ratio or proportional. So it's kind of like, instead of with congruent figures, you would put a figure on a copy machine and press start, and it would make an identical copy. Well, with similar figures, it would be like you're enlarging something or shrinking something on a copy machine. The angles all stay the same, but the sides are like either twice as big or half as big. That's kind of what happens with similar. Now, there is a symbol for similar. Okay, and it's a tilde, and that means, that symbol means similar. So the first example we have here, it says write a similarity statement about the triangles. Well, first of all, we can see that all the angles are marked congruent. So the angles are congruent. Now, if we look at the corresponding sides, if we look at this side right here, it's between the 1 and 2 tick mark angle, and so is this. So we look at that ratio of sides, and that's 6:3, or if we reduce that, it would be 2:1. So now let's look at the ratio of another side between the 2 and the 3 tick mark angles right here. That ratio of sides is 8:4, which is also 2:1. So this is what we mean when the sides are in the same proportion. 2:1 is the same as 2:1. And if we look at that last side between the 1 and the 3 tick mark angle, that has a ratio sides of 12:6, which is also 2:1. So again, we now know we can actually state and say that the triangles are similar. So the statement that we would write is kind of similar to a congruent statement. We would say that triangle ABC is similar. And again, order matters, just like in congruent figures. Angle A has to be corresponding congruent to angle D. So we have to name it in that same order. So D, since B and E correspond, we would name this D, E, F. And that is a similarity statement. So if we look at the second example, we can see that it's listed that the figures are similar. That's what that symbol means, is similar. That's the similar similarity or similar symbol. So the congruent angles would be angle W is congruent to angle M. And angle X is congruent to angle N. Angle Y is congruent to angle O, and angle Z is congruent to angle P. So how do I know that? Because of this similarity statement, okay, it tells me that X and N are the ones that are corresponding and congruent. It also tells me something about the sides. So this next question asks us to write the ratios of the corresponding sides in a similarity statement of proportionality. This is a similarity statement up here. WXYZ is similar to MNOP. So the ratio of sides that would be in the same proportion would be that WX right here is in the same proportion. When you take WX, the ratio of WX over MN, that's going to be in the same ratio as XY compared to NO, their corresponding sides, which would be in the same ratio as YZ compared to OP, would be in the same ratio as WZ compared to MP. And that is a statement of proportionality of the sides. Now, sometimes people get confused if there are values assigned to them, but normally we write this statement of proportionality with the actual sides from the similarity statement. So, here's a question that's asking you, if triangles A, B, C, and D, E, F are similar, which statement is not correct? Well, AB compared to DE should be the same ratio as BC to EF. So that is true. CA, so CA compared to FD would be in the same ratio as AB to DE. So that's true. And then the last thing says angle A and angle F. Well, angle A right here should be corresponding and congruent to angle D, not F. So that is false because angle A should be congruent to angle D. So now let's talk about scale factor. So the scale factor is the ratio of the lengths of the two corresponding sides in a similar polygon. So basically we could write the scale factor as like 2.6 compared to 3.9. That's the ratio of the sides. But it's kind of also, which if we reduce that, it's approximately 0.6. But the scale factor is also thought of as how many times bigger or smaller a figure is. So when I use that copy machine example, every side might be twice as big, or every side might be half as big. So that's kind of the same thing as scale factor. So the question asks, what is the scale factor of triangle 1 to triangle 2? Notice it's going triangle 1 over to triangle 2, so we have to list it in that order. So again, I wrote it down here. Here's triangle 1 compared to triangle 2. And we can see that the ratio is 2.6 to 3.9, which is kind of hard to understand, but basically it's congruent to 0.6. So that means triangle 2 is 60% larger, or 0.6 larger. And if they ask us from 2 to 1, then it would actually be flipped and reversed. So keep that in mind. This is important that they're asking it in this direction so that you make sure you understand how to write the ratio of those sides. Now, if they don't give you specifically, they just say, what is the scale factor? Then you are certainly able to write it either way. So let's see if we can determine, are these polygons similar? And if yes, we're going to write a similarity ratio and find the scale factor. Well, the first thing I look for when trying to determine if two polygons is similar is look for all angles to be congruent. Well, angle B is not congruent to angle E because this is marked as 1 tick mark and this is marked as 2. So see, already right now we don't have congruent angles. So these are not going to be similar because we do not have congruent angles. So we don't have to write a similarity statement or a similarity ratio or a scale factor. So let's look at these two polygons. Well, I can see that we have 4 right angles here, 4 90-degree angles, and same here. So we do have congruent angles. So now we need to check the sides. So we have to see if side here, the largest side compared to the largest side, so 24 compared to 6, is that equal to the smaller side compared to the smaller side, so 16 over 4. Again, notice I have to make sure that I'm writing them large to small, and since both those equal 4 over 1, then yes, they're similar. So now we're going to write a similarity ratio. This is actually a similarity statement that we want to write. I think that will be more helpful. So now we can say that polygon W, X, Y, Z is similar to D, A, B, C. And the scale factor, if I go from this figure to this figure, would be 4 to 1 is the scale factor. Okay. So let's talk about this example here. It says find the scale factor of MN or WXYZ to MNOP. So again, notice we're writing it in that order. It already tells us that these are similar. We can see that from that marking. So now I need to write the scale factor of the sides of one pair of similar sides. Well, if I try to go WX compared to MN, I don't know MN. That is unknown right here. So let's find a different pair of sides if we can. Well, if we use XY compared to NO, we do have XY is 8 and NO is 10. So the scale factor is 8 to 10, which we always rewrite it as the ratio in reduced form, so 4 to 5. So now let's find the perimeter of WXYZ. Well, in order to find the perimeter, I need to find this side Y right here. Well, side Y right here corresponds to WZ. So WZ would be the same as MP. So MP right here is 10. So that means that the ratio of sides has to be the same as 4 over 5. So that means that 4 over 5 has to be the same ratio as what we don't know, Y to 10. Now we can cross multiply and we get 40 equals 5Y. So Y equals 8. And you probably just wanted to guess that, but we should always do the actual math to make sure. So now the perimeter of WXYZ is equal to, if we add all those sides together, we get 40 units. So now we're going to find the perimeter of MNOP. So MNOP, we already know is 10 and 10. We need to find MN, and that's going to be in the same ratio. Remember that MN is corresponding and going to be the same ratio of sides as WX. So what we know is that the ratio of WXYZ side, or WX, 12 over X, has to be in the same ratio as 4 over 5. So again, cross multiplying, we get 60 equals 4x, so x equals 15. So this is 15, and we could probably just use common sense. Since these two are the same and these two are the same right here, then the corresponding sides would also have to be the same. So the perimeter of MNOP is equal to 50 units when we add all those together. So now notice, if we write the ratio, we wrote the scale factor, or we wrote the scale factor of WXYZ to MNOP was 4 to 5. Well, look what happens to the perimeters. If we write that same ratio, the perimeter of WXYZ to MNOP would be 40 to 50, which is also 4 to 5. And that's kind of a significant piece to similar figures. Now the question below actually asks us to write the ratio of the perimeter of MNOP to WXYZ. So we would actually write it as 50 over 40, which is 5 to 4. So this is our perimeters of similar polygons theorem. It says if two polygons are similar, then the ratio of perimeters is equal to the ratio of the corresponding side lengths. So all we have to do is, if we know the ratio of side lengths, then we also know the ratio of the perimeters. So the ratio of one side of ABC, triangle ABC, to the corresponding side of similar triangle DEF is 4:3. So we have the ratio of sides is 4:3. If the perimeter of DEF is 24, what is the perimeter of ABC? Well, we know the ratio of ABC to DEF is 4:3, and the perimeters will also be in that same ratio. So 4:3 is going to be the same ratio of the perimeters. So I know the perimeter of DEF, that's on the bottom, that's 24. I'm trying to find the value of the perimeter of ABC, that goes on the top, because remember, we had ABC over to DEF. So now I just cross multiply and solve, and I get x is equal to 32. So that means the perimeter is equal to 32 inches. So it would be choice C. All right, we have one more example to go through in this lesson. It says the community park has a rectangular swimming pool enclosed by a rectangular fence for swimming, or for sunbathing, excuse me. So you have a swimming pool and you have a concrete area or whatever for just laying out in the sun. The shape of the pool is similar to the shape of the fence. The pool is 30 feet wide, the fence is 50 feet wide and 100 feet long. So what is the scale factor of the pool to the fence? Well, first of all, if we draw this, okay, we have a fence and it says it is 50 feet by 100 feet. That's the fence. And then enclosed in it side, you have the pool. And that is 30 feet wide. So we want to know the scale factor of the pool to the fence. And so what we know is that the pool is 30 feet and the fence that corresponds is 50 feet. So that is going to give us a ratio or a scale factor of 3:5. So now we're going to use that to find the length of the pool. So we're trying to find this length of the pool x. So we know that the ratio of sides of the pool to the fence, again, pool to the fence is 3:5. And since we're trying to find the pool's length, we do know the fence's length, then we can set up the proportion and solve. So that gives us x equals 60. So it says find the area reserved strictly for sunbathing. So what we're looking for is we're looking for this area right here. That's what we're trying to find. That's the sunbathing area right there. Area outside the pool, but still in the fence, side the fence. So what we do is we are going to find the area of the fenced in, and we're going to subtract the area of the pool. Well, the fenced in area is 100 times 50. The area of the pool is 60 times 30. So that gives us 5,000 minus 1,800, which is equal to 3,200 feet squared. All right, that is the end of section